In this session of coordination compounds, I am going to speak about crystal field theory in a complex like tetrahedral complexes. I am going to discuss now crystal field splitting in a tetrahedral complex. In the previous session, I discussed crystal field splitting in octahedral concept, and we have drawn the energy level diagram of that, and especially I discussed the postulates of crystal field theory that is going to be holds good for octahedral molecule, tetrahedral molecule, or you can consider square planar molecule also. Tetrahedral complex, how actually the tetrahedral complex looks like, you need to remember. M is considered to be the central metal atom, and in a tetrahedral complex we have a central metal atom which is surrounded by 4 ligands. So one we have in this fashion and the remaining 3 will be in this fashion, means all the 4 ligands are going to occupy at the 4 corners of the tetrahedron shape. So that actually how tetrahedral complex looks like. Remember that in coordination complex whose shape will be tetrahedral, in that case the central metal atom is surrounded by 4 ligands. As we know, if you consider only the transition element, the atomic orbitals are degenerate. Atomic orbitals with identical energy, we call it as degenerate. And how the ligands are going to approach towards the central metal atom, in particular d orbitals, that depends on which set of d atomic orbital is going to experience more repulsion and less repulsion. Why actually repulsion occurs? D atomic orbitals contains electron and the ligands also contains electron. Since we have electrons in transition elements, in particular d atomic orbitals, and electrons in case of ligands also, when they will be approaching of these two, then both contains same charge electron cloud, therefore repulsion is going to take place. The same point I have mentioned, repulsion between electrons of d orbitals and electrons of ligands. So there will be repulsion. Then as we know, when the central metal atom is going to approach the ligands, then the degeneracy of the d atomic orbital is disturbed. The degenerate d atomic orbitals lifted up and they undergo splitting, so that to form 2 sets of d atomic orbitals, we call it as T2g, and one more we call it as Eg. But which experience more repulsion, which experience less repulsion, depends on which set of atomic orbital is going to approach along the axis and in between the axis. So remember that if any d atomic orbital, if they are towards the ligand, and they are going to experience more repulsion. If the d atomic orbitals, if they are away from the ligand, they are going to experience less repulsion, because if the distance between the ligand and central metal atom is more, or I can say they are towards, the d atomic orbitals and ligands are towards, of course the distance is less, means repulsion will be definitely greater, because the charge of both are the same. Negatively charged cloud we have when we have d atomic orbitals and ligands away, and repulsion is minimized. So that is the main concept from which we can identify which has more repulsion and which has less repulsion. Remember that in case of tetrahedral complex, T2g atomic orbitals, they are going to experience more repulsion, whereas Eg atomic orbitals, they are going to experience less repulsion. Remember that this is exactly opposite in case of octahedral complex. In case of octahedral complex, Eg atomic orbitals used to experience more repulsion, whereas T2g atomic orbitals used to experience less repulsion, whereas in case of tetrahedral, T2g experiences more repulsion. Why T2g experiences more repulsion? Because in a tetrahedral complex, T2g atomic orbitals are approaching towards the ligand. These ligands, these atomic orbitals, d atomic orbitals nearer to the ligands, therefore repulsion will be more. When repulsion will be more, the energy is ultimately high. Whereas what actually the second one, Eg atomic orbitals, they are going to experience less repulsion, because in tetrahedral complex Eg atomic orbitals are far away, therefore that is going to experience less energy and it has a less energy for that. But if you observe, I have not considered T2g, I have not considered Eg. Instead of that, I have written a T2 and E. I hope you remember the reason what I explained in the previous session. The G term what I use in case of octahedral complex indicates the complex has a center of symmetry. Since in case of tetrahedral complex we don't have any center of symmetry, therefore I have not represented G, just I have represented T2 and G here to indicate that the tetrahedral complex is not going to possess center of symmetry, whereas octahedral complex they used to possess center of symmetry, therefore I used to write T2G and EG. For tetrahedral complex it is represented as a T2 and E only. Remember that in tetrahedral complex T2 will be having more energy and E will be having a less energy. Of course, when degeneracy of d atomic orbitals are lifted up and splitted, from this concept we know that T2 will be at higher energy and E will be at lower energy. The difference between these two energy levels T2 and E, that we call it as crystal field splitting energy. Crystal field splitting energy, in general we write this symbol delta. In case of crystal field splitting energy of octahedral complexes, I would have written O, which represents octahedral complex. Since I am going to talk about tetrahedral complex, so let me write a T here. So delta T stands for crystal field splitting in tetrahedral complex. So which is equals to arbitrary value is 10 dq. It is also as same as the octahedral complex. So delta T is equals to 10 dq. 10 dq is the magnitude or arbitrary value of crystal field splitting in case of tetrahedral complex. Now you remember, as I said, T2 energy is going to increase. How much energy is going to increase? And Eg energy is going to decrease. What is the value of decreased energy? Remember that the T2 atomic orbitals are going to increase with the factor 2 divided by 5 delta T, or you can say 0.4 delta T, or you can say 4 dq, as same all the three. Since delta T is equals to 10 dq, you can write 0.4 delta T in the form of 10 dq also. E atomic orbitals are going to possess less energy than degenerate atomic orbitals, and the factor will be 3 divided by 5 delta T, or 0.6 delta T, or 6 dq you can say here. So the T2 will be higher and we have to mention the energy change, that is 2 divided by 5 delta T, and E will be lesser, and that we represent it as T by 5 with the delta T. So now if you know this concept, now I am going to know with the diagrammatic representation of crystal field splitting in case of tetrahedral concept. So as we have seen in case of octahedral, so what we did actually, and initially I considered 5 degenerate orbitals, metal d atomic orbitals, and energy is increased from bottom to top, and when the transition metal or the d atomic orbitals of d block elements is going to approach the ligands, then the lifting up of atomic orbitals takes place. So next I will draw 5 atomic orbitals which has higher energy than the original one, and then splitting up of degenerate atomic orbitals takes place, and in a tetrahedral complex I need to represent T2 above, I need to represent E below, and will write the respective terms involved in that one. So now I am going to do that. So what I consider the 5 horizontal lines, and these are going to represent the 5 atomic orbitals of D, and they are degenerate. So what are these? These are actually metal d orbitals. These are metal d orbitals. In general, energy is going to vary in this fashion. From bottom to top, the energy is going to change. And we know already what are these d atomic orbitals. One is dxy, one more is dyz, and dxz, and dx square minus y square. and dz square, 5d atomic orbitals of identical energy, therefore that we call it as the degenerate atomic orbitals. When the central metal atom is going to approach towards the ligand, then there is an interaction between the central metal atom as well as the ligand, therefore energy is going to lifted up. So higher energy level I am supposed to draw here. So just to see how I am supposed to draw. So 5 lines I am going to draw here that represents the higher energy level, and this is average energy level, and the energy is going to lifted up. So I represent these dotted lines to indicate that the energy has been increased, means the d atomic orbitals has been lifted up due to the approaching of a central metal atom towards the ligand. Not only the energy level is lifted up, but also splitting occurs here. And if splitting occurs, we get two different set of atomic orbitals, T2 and E. And in case of octahedral, we used to draw Eg above and we used to write T2G above. But in case of tetrahedral, it is exactly opposite as I mentioned. Therefore, T2 we get above and E we get below. And the reason, you know, when the central metal atom is going to approach towards the ligand, in case of tetrahedral complex, T2 atomic orbitals is going to experience more repulsion. Since more repulsion it experiences, therefore the energy will be higher. Why actually T2 atomic orbitals will experience more repulsion? Because in the tetrahedral complex, T2 atomic orbitals are nearer to the ligand, whereas E atomic orbitals are far away from the ligand. Therefore, T2 experiences more repulsion. More repulsion means high energy. Therefore, T2 I will draw here and E I am supposed to draw here. So, T2 as it contains 3 atomic orbitals. So, 3 I am supposed to write here 1, 2 and 3, and one more will be that is of Eg, isn't it? So Eg I am supposed to draw here. So this is T2 and this will be E. I won't write T2G, I won't write Eg because center of symmetry is absent in case of tetrahedral complex. If you consider this is the average energy, and now we'll see this is the higher energy level T2 and this will be the lower energy level E. The total energy difference between T2 and E in case of tetrahedral complex, we call it as the delta T, which indicates crystal field splitting in a tetrahedral complexes. T2 we have 3 atomic orbitals dxy, dyz and dzx. In case of E we have only 2, dx square minus y square and dz square, and we have seen the shape of these atomic orbitals in the previous session. Now the energy gap in between T2 and V, we call it as delta T, crystal field splitting in case of tetrahedral complex. But how much energy has T2 has been increased, and what about the E? So try to remember the T2 is going to increase by a factor 2 divided by 5 delta T. Remember that 2 divided by 5 delta T is going to increase. Then what about the decrease in the energy of E? That will be 3 divided by 5 delta T I can write. So see here, in case of T2 we have 2 by 5 delta T, in case of E 3 by 5 delta T, and if you draw the diagram and the magnitude, or you can say that should be suitable. See here, quite less energy level we have, and here we have greater energy level because Eg for E 3 by 5 we have, and for T2 2 by 5 we have, and it is actually the average, and the energy of T2 is higher than this average degenerate d atomic orbitals, and energy of E will be lower than degenerate atomic orbitals, and this will be original degenerate d atomic orbitals, that is completely lower when compared to that. This is the reason I mentioned from bottom to top the energy is going to increase. So this is the degenerate d atomic orbitals, and this is average degenerate d atomic orbitals, and this will be T2 since it has dxy, dyz, dzx, and this will be E dx square minus y square and dz square, and the magnitude of a change in the crystal field splitting I have mentioned here. And in this case the question arises, If you consider the electrons into the different atomic orbitals, as I said, usually we represent in this manner: 1, 2, 3, 4. This same representation I have written: average degenerate atomic orbitals, and higher energy will be of T2. So T2 has 3 and E will be of only 2. So this will be T2 and this will be E. And now the question arises, how we are supposed to fill the electrons? So remember that here we have one condition. What is that condition? If delta T is less than P, delta T, crystal field splitting in case of tetrahedral complex. So P stands for pairing energy. Remember that P stands for pairing energy. The energy required during the pairing of electrons, we call it as pairing energy. If tetrahedral splitting is less than P, and what happens actually here, the ligands are going to be weak filled ligand, and the complexes what we are getting, and they are high spin complexes. So what is the meaning of that? We have only one condition. In case of previous crystal field splitting theory, in case of octahedral complex, we used to write two conditions: delta O is less than P and delta O is greater than P. But here we have only one condition, means in case of tetrahedral complex, only high spin complexes are formed. So if this is a condition, of course usually in general the ligands will be of weak filled ligands and high spin complexes are formed. So weak filled ligands we have, means here in this case the electrons to be added as it is according to the rule. There is no need to change the rule here. So remember that this condition is going to be satisfied. Only high spin complexes are formed in case of tetrahedral complex. This is the very important point. Remember, in case of octahedral, it depends on what kind of ligand we have, and it depends on the change in pairing energy whether we get a high spin complex or low spin complex, whereas in case of tetrahedral complex only high spin complexes are possible, because always the crystal field splitting energy of tetrahedral complex is less than. So this difference will be very less. So if this difference is very less, then what happens here? The one more electron what we consider, that is going to enter into T2G atomic orbital. As I said, if you consider a D3, okay, and then what happens? We are supposed to fill this one, and one more electron is going to fill in this case, because this crystal field splitting is very less when compared to pairing energy. So here 2 electrons I am supposed to fill here, and the third one I am supposed to fill in a T2. Because of that reason only high spin complexes are formed in case of tetrahedral complex. That is all about crystal field splitting in case of tetrahedral complex. So now let me compare the octahedral complex and tetrahedral complex. The difference you try to remember that. In octahedral complex, central metal atom is surrounded by 6 ligands, whereas in tetrahedral complex the central metal atom is surrounded by 4 ligands. In both cases, when the central metal atom of d atomic orbitals, especially when they approaches the ligand, there will be interaction, and the electron cloud we have in both cases, therefore repulsion is going to occur. In both the cases, if we have d atomic orbitals towards the ligand, repulsion will be more. In both cases, when we have d atomic orbitals away from the ligand, the repulsion will be less. Remember, in octahedral complex, EG experiences more repulsion, therefore high energy. T2G experiences less repulsion and less energy, whereas in case of tetrahedral complex, T2 experiences more repulsion, high energy. E experiences less repulsion, less energy. Remember, in a T2G we have a set of 3 atomic orbitals, dxy, dyz and dzx, whereas in case of EG we have only 2, dx square minus y square and d z square. Depending upon that, we used to draw the energy level diagram of that. And what is the change in energy? The difference between these 2 energy levels, we call it as crystal field splitting energy. If you write a delta O, crystal field splitting in octahedral complex, delta T, crystal field splitting in a tetrahedral complex. And the energy change you need to remember, in case of EG or E, You can say 3 divided by 5 delta in general. In case of T or T2G, 2 divided by 5 delta in general. And the energy difference we need to mention there. And the concept of pairing energy will be significant in case of octahedral complex, because when delta O will be greater or less than pairing energy, that decides which complex is high spin complex and which one is a low spin complex, depends on what kind of ligand we have, whether we have strong ligand, whether we have weak ligand. In case of tetrahedral splitting, there is possible of high spin complexes only, means usually the tetrahedral complexes are of weak field ligands. In this case, delta T will be less than pairing energy, and usually the pairing energy is not significant in case of tetrahedral complex. And if you just remember one diagram, if you interchange these two, and that would be the diagram of octahedral geometry, octahedral complex, and the degenerate orbital means atomic orbitals of identical energy, we call it as a degenerate. When the central metal atom approaches the ligands, then lifting up and splitting up of d atomic orbital takes place. That is the reason why actually we write the 5 d atomic orbitals in the set of 3 and in the set of 2. But if you compare the crystal field splitting energy in octahedral complex and crystal field splitting energy in tetrahedral complex, the magnitude of tetrahedral complex is quite less than magnitude of octahedral complex. What is that magnitude? Crystal field splitting of tetrahedral complex is nearly equal to 4 divided by 9 into delta T naught. Remember that one. So that is the relationship between the crystal field splitting energy in case of octahedral complex and in case of tetrahedral complex. Remember that when you compare tetrahedral and octahedral, crystal field splitting in case of tetrahedral complex is less than octahedral complex, and the ratio we can mention in the ratio of 4 divided by 9. So the question arises, why actually the tetrahedral splitting is going to be magnitude less when compared to the octahedral? We have the reasons for that. The main reason is, remember that in case of tetrahedral complex we have only 4 ligands, whereas in case of octahedral complex we have 6 ligands. That is the first reason. One more reason is, in case of octahedral complex, we have atomic orbitals along the direction of the ligands, that is more significant. So because of these two reasons, the crystal field splitting in case of tetrahedral complex is quite less than crystal field splitting in case of octahedral complex. One physical property of a coordination compound which is not explained by valence bond theory and explained by crystal field theory is color. Coordination complexes possesses color. According to crystal field theory, we have the explanation why actually the coordination complexes are going to possess the color. When white light is passed into sample of coordination compounds, the coordination compound is going to observe suitable wavelength of light, and the remaining wavelength is going to be emitted by the coordination substance, and the emitted wavelength is going to be responsible for the color of the coordination complex. If I consider any example of coordination compound and I am going to pass white light over there, then the coordination compound is going to absorb the certain wavelength of light, and it absorbs certain wavelength of light, and light has more wavelength as compared to the absorbed wavelength. So the remaining wavelength will exist as a mixture, and that wavelength color is going to be emitted. In simple, you remember, the color of the complex is not because of the wavelength of light what it absorbs, it because of the color of wavelength what it emits. Example we'll see. If I consider the example of CuNH3 4 times, cation complex, the charge is 2+. Central metal atom is copper, and the ligands are NH3, and if a white light is passed into aqueous solution of this particular compound and it absorbs wavelength which is suitable to red light, it absorbs the wavelength which is suitable to red light, and red light wavelength it is going to absorb, and the remaining wavelength is going to be emitted. So it emits a certain kind of wavelength, okay, and that will be of the region corresponds to blue. Therefore the color of this particular complex is blue. So blue is said to be the complementary color of red. The word what I use, try to understand. Blue is the complementary color of red. Why? Because the red color is going to be absorbed by the complex and the blue color is going to be emitted by the complex, and the color emitted will be responsible for the color of the coordination compounds. Therefore blue color is the complementary color of red, and this particular compound has a blue color. Any compound if you consider, and if it absorbs the wavelength of red color and it is going to emit the wavelength of blue color, the color of the substance will be blue. One more example, TiH2O 6 times, the charge will be of 3+. When white light is passed into aqueous solution of this particular coordination complex, then this complex is going to absorb blue-green color, and when this particular complex absorbs blue-green color, and it is going to emit a wavelength of violet color. Therefore the color of this particular complex is violet. So violet is the complementary color of blue-green, and blue-green color suitable wavelength has been absorbed, and the wavelength of violet color has been emitted. Therefore the color of this particular complex is violet. Why there will be such kind of absorption, why there will be such kind of emission of wavelengths? So that the coordination compound is going to possess a color. The reason behind this is DD transition. As we know, the transition metal ions are going to possess a DD transition. Because of that, the particular complex or a coordination compound is going to possess the color. So how DD transition can be explained? See, I am going to consider this particular example. So the second example, if you consider, the charge will be 3+, and H2 is a neutral molecule 0, I will write. Therefore the charge of Ti will be 3+. Titanium, Ti we have, and atomic number of Ti will be 22, because 21 is scandium and 22 will be titanium, then vanadium, and it will continue 3D series of D block elements. For Ti, the electronic configuration is argon 3D2 and 4s2, but in this particular compound we don't have Ti, we have Ti3+. So if you have Ti3+, the electronic configuration will be Ar, and 3 electron has been lost, 2 from here and 1 from here. We are supposed to left with 3D1 and 4s0. So we have a 3D1. In a 3D atomic orbital, we have unpaired electron, and that is going to be responsible for the color of this particular complex. So how DD transition takes place in case of 3D1 and 4s2? Remember, this particular compound is a coordination complex. What is the coordination number? Coordination number is 6. According to crystal field theory, if the coordination number is 6, we need to consider crystal field splitting in case of octahedral complex. And recently we studied about crystal field splitting in case of octahedral as well as tetrahedral. In case of octahedral complex, the d atomic orbitals are going to lifted up and they split up. And in octahedral complex, Eg is going to have higher energy and T2g is going to have lower energy. Therefore, now I am drawing the d atomic orbital of Ti3+. So now see here, this will be, I will draw only the splitted up energy levels. This will be Eg, isn't it? And we have a T2g. So in Eg, 2d atomic orbitals we have. In case of T2g, Eg we have. So this is Eg and this is T2g. So dx square minus y square dz square, dxy, dyz and dxz. So this is how the electron is going to be, the d atomic orbital is going to be splitted up. How many electrons we have in the 3D one? We have only one electron. So in which atomic orbital you are supposed to fill the electron? So according to Aufbau principle, we are supposed to fill to the lower energy first. Therefore only one electron we have. So therefore I am going to write this presence of one electron in this case. That is actually the energy level diagram. And how does the electrons are going to be filled up in case of Ti3 plus, since the configuration is 3D1. What happens when you consider this particular complex, and when you pass white light of a suitable wavelength? So white light, if you pass of h nu, where h is Planck's constant and nu is frequency of radiation, in that case what happens, this particular central metal atom, this particular 3D atomic orbital, it absorbs the wavelength of a suitable light. So wavelength of suitable light, in particular wavelength corresponding to blue-green, it is going to be absorbed, and in that case the electron is going to possess a kind of energy. So when energy is supplied to the electron and the electron is going to be excited, therefore there will be shift of electron from T2G level to EG level. How actually shift of electron takes place? So this will be EG, and this what I am drawing now, that is of T2G, and this is EG and this is T2G. Let me write here. And this is how we have one electron. When a light of a suitable frequency h nu is going to fall over this particular compound, and electron from T2G is going to shifted into EG. So now after passing white light, the electron will be here. So why there is shift of electron from lower energy level to higher energy level? Because there will be absorption of energy, and after this particular compound is going to emit a radiation of suitable frequency. Then again the electron which is present in higher energy level, that is going to be shifted to lower energy level, and the corresponding radiation, corresponding light what it emits, corresponding wavelength what it emits, it is of the suitable of a wavelength. Therefore there is a transition of electron from one d atomic orbital to one more d atomic orbital. Therefore this kind of transition we call it as a dd transition. Remember that. This kind of transition we call it as a dd transition. I hope you remember, while dealing with the D and F block elements, the D block elements are colored. The main property is the dd transition. We used to only say that dd transition. And now what actually dd transition? Remember that in case of D we have EG and T2G. This is how the one electron from one energy level or lower energy level is going to be shifted to higher energy level. Such kind of transition of electron in between the d atomic orbitals, we call it as the dd transition. So in both the cases there will be dd transition. Because of that, the coordination compounds are going to possess a certain kind of a color. One thing you remember, here I consider two examples. So now let me consider example and we'll see the reason later. So now if I consider example of CuSO4, and if I consider example of CuSO4 5H2O. So this CuSO4 5H2O, the color is blue, whereas CuSO4 is colorless or white. I will write here. Let me write, consider it as white color. In general you can consider it as colorless also. So what is the difference between these two? So we have the explanation according to crystal field theory again. Remember, in this particular compound CuSO4 5H2O, H2O acts as the ligand. I can write in one more fashion also. What is that? Cu H2O 5 times, coordination sphere, SO4 outside. So here we have ligands, and in the CuSO4 we don't have ligands. What I am going to say here is the compound will be colorless in absence of a ligand. I repeat, the compound will be colorless in absence of a ligand. Why? In absence of ligand, there will be no splitting of d atomic orbitals. We have only degenerate d atomic orbitals. In the presence of ligands only, the degeneracy of atomic orbitals are lifted up and they are supposed to be splitted. So because of that reason, since the second compound has ligands, therefore it has a certain kind of color, that is a blue color. So blue color is the color emitted by this particular compound, and the wavelength of suitable absorbed will be red, because complementary of red will be blue, and whereas this particular compound is going to possess a white colored light. And you can perform the same kind of test in the lab also. It is very simple. So CuSO4 5H2O, blue vitriol we call it as, blue colored crystal it is. So if you observe the blue colored crystal of CuSO4 5H2O, it is blue colored. What I consider? I consider a test tube and supposed to add the blue colored CuSO4 5H2O into the test tube. And what I do, using test tube holder, I am supposed to heat the test tube. And after heating, suddenly what you observe is the blue colored CuSO4 5H2O is going to be converted into white colored substance. The blue color is going to be converted into white. Why? Because during heating, this water of crystallization will undergo evaporation. So H2O, this crystal has a little content of water, that we call it as water of crystallization. Water of crystallization is removed. Water of crystallization is removed means ultimately we are going to remove the ligands. If we don't have ligands, and then ultimately the color will be white. So if you have a white colored CuSO4 and just you add 1 or 2 drops of water into the test tube, again that is reversible, you will be getting the blue colored CuSO4 5H2O. Remember that the coordination compound or the complex will be colored only in the presence of ligand. Why? Because in the presence of ligand, the degenerate orbitals are going to split it up as Eg and T2G. That is all about the property of color, which is explained by crystal field theory, and this property is not going to be explained by valence bond theory. That is the best demerit of valence bond theory, you can remember. Now we'll see a kind of concepts related to carbon monoxide as ligands, and that I call it as metal carbonyls. Bonding in metal carbonyls. Bonding in metal carbonyls. Let me write that. What actually the metal carbonyl stands for? Organometallic compounds. Organometallic compounds with carbon monoxide as ligand. Carbon monoxide as ligand, we call it as organometallic compounds. As the name indicates, organometallic compound, organic type of carbon we have in the ligand. Apart from that, we have a metal over here. So the central metal atom is going to be surrounded by a type of ligand that we call it as the carbonyl, carbon monoxide in general. So such kind of organometallic compounds we call it as the metallic carbonyls. One example I consider, NiCO4 times. Tetracarbonyl Nickel is the name. This is a neutral complex as we know. So here nickel as a central metal atom and carbon monoxide, in particular carbonyl, acts as a ligand here. So if we have a central metal atom which is surrounded by carbonyl as a ligand, and we have a special kind of that we call it as the organometallics, or I can say metal carbonyls. And remember, these organometallic compounds or metal carbonyls, they are going to possess both sigma and pi character. Remember that. They are supposed to possess both sigma and pi character. So sigma bond is formed by head-on overlapping of atomic orbitals, whereas the pi bond is formed by sideway of overlapping of atomic orbitals. We know. So in the metal carbonyls, we have sigma character as well as the pi character. Then question arises, how in a same kind of compound we have both sigma character and pi character? Remember that carbon monoxide, how we write carbon monoxide? This is actually, we write the carbon monoxide. In the carbon monoxide, in between carbon and oxygen, we have triple covalent bond, and that is actually the ligand, carbonyl. We have central metal atom. Let us assume we have M. M stands for central metal atom. So we have a carbon and we have a central metal atom. Carbon of carbonyl and central metal atom particular of transition element. In this case, what happens? This ligand contains lone pair of electron. So here this ligand is going to donate the lone pair of electron into vacant hybrid orbital of metal, so that there will be a formation of a sigma bond in this fashion. So opposite of that, I consider metal and I consider carbon of carbonyl. So apart from that, in the pi atomic orbital of a metal, it has pair of electron, so that is going to be donated to the pi star atomic orbital of carbon monoxide by sideway overlapping. Therefore pi bond is going to be formed. So we have a bond between carbon to metal as well as the metal to carbon, and because of that reason we have sigma character as well as a pi character. Let me explain the same concept using the atomic orbital diagram. See here, M stands for central metal atom, remember, and C stands for carbon of carbonyl, right? And I will draw the respective atomic orbitals only. This is what actually the atomic orbital, vacant atomic orbital of a central metal atom. And here I will consider one more atomic orbital of this particular carbon. So in this case what happens, this particular metal orbital, so it contains what actually the lone pair of electrons. So let me draw here. So this is the vacant atomic orbital, and now this will be head-on fashion of overlapping, isn't it? And apart from that, this particular carbon has the sideway overlapping in this fashion. So let me draw the remaining also. These are the atomic orbitals, and for the metal we have atomic orbitals here, and we have atomic orbitals in this fashion. So what I am going to say, this atomic orbital of central metal atom is vacant, which is hybrid, whereas this atomic orbital of carbon monoxide contains a lone pair of electron. So this pair of electron is going to be donated to this central metal atom so that the sigma bond is formed. Try to understand, the lone pair of electron is carbon is going to be donated to the central metal atom, what I indicated here, and because of here there will be head-on overlapping of atomic orbitals, therefore sigma bond is formed. Apart from that, these are the pi atomic orbitals. So pi atomic orbitals of this particular central metal atom is going to possess the lone pair of electron. This will be pi of central metal atom, this will be pi star of this carbon of carbonyl. So this particular lone pair of electron is going to be donated to pi star atomic orbital of carbon. So here there will be sideway overlapping. As we know, if you consider the p atomic orbital, we have two loops. So this is how sideway overlapping, this is how sideway overlapping, together loops overlapping, we call it as one pi bond. Therefore this is how overlapping takes place. Because of that reason the pi bond is going to be formed. So we have sigma characteristics as well as the pi characteristic. Sigma bond, in that case there will be donation of a lone pair of electron from ligand to the central metal atom. The pi bond, in that case there will be donation of lone pair of electron from central metal atom to the ligand. In case of a sigma bond, head-on overlapping. In case of a pi bond, we have sideway overlapping. So in this case, the sigma bonding is going to strengthen the pi bonding, and also pi bonding is going to strengthen the sigma bonding. So because of that, these two are going to strengthen each other characters. Because of this reason, this kind of bonding we call it as synergic bonding. So synergic bonding is going to occur in case of organometallic compounds or metal carbonyls. So sigma bond is going to strengthen pi bond, as well as pi bond is going to strengthen sigma bond. Because of this one, I use a name, we call it as a synergic bonding. Because of this reason, such compounds are quite stable, and this kind of diagrammatical representation to explain why we have sigma bond as well as why we have pi bond character in case of metal carbonyls. Examples for metal carbonyls. Central metal atom has to be surrounded by a kind of ligand, carbon monoxide or carbonyl. And the bonding also we know, we have sigma characteristics as well as pi characteristics. Remember the carbon, what I have written, actually this is the carbon which is going to be triple bonded with oxygen, and it has the 3 atomic orbitals. I mentioned carbon only, but it is carbon triple bond oxygen in general if you represent the diagrammatical representation of that. So now we'll see one particular example. So one simple example I have written, Tetracarbonyl Nickel. So we'll see the structure of that one, how actually Tetracarbonyl Nickel structure we have. So we have a nickel is a central metal atom which is surrounded by ligand, and the coordination number we have 4. And therefore here the carbon monoxide or carbonyl are going to be situated in this fashion four corners of the tetrahedron. Remember that there is a bond between carbon of carbon monoxide with the nickel only. So carbon with the nickel. Therefore, I have written carbon monoxide or carbonyl in this fashion, because as we know, in case of bonding, we have the atomic overlapping in between carbon and central metal atom only, and the shape of this will be tetrahedral, and the molecule is actually CnICO 4 times. One more example I consider, that will be FeCO 5 times. Central metal atom is iron. So central metal atom iron I consider, and we have carbonyl in this fashion. So trigonal planar you can say, and one will be above and one will be below, and the shape of such kind of geometry we call it as trigonal bipyramidal. So we can write these two carbon monoxide or carbonyl here and one carbonyl here, but it is of the trigonal fashion, and one will be above and one will be below. That is nothing but the trigonal planar, and if you consider one above one below, and that geometry or the shape we call it as trigonal bipyramidal geometry. One more example I consider, CrCO 6 times. Coordination number is 6. One can easily guess the geometry would be octahedral. Therefore, 4 carbonyl will be the 4 corners of the square, and one carbonyl will be above and one carbonyl will be below, and that kind of geometry we call it as octahedral geometry. And one more example I am going to consider, that is a special example. So Mn2CO10. One more example I will be considering, CO2 and CO8. So Mn manganese carbonyl we have, and C small o cobalt, capital C capital O carbonyl. So now I am going to draw the diagrams of these two. If you observe the previous diagrams and the 3 diagrams what I have written above, and in all these cases we have only one central metal atom, transition element we have only one, whereas here we have 2 Mn and here we have 2 cobalt, means ultimately this suggests us that there is a bonding between a metal to metal. So in between metals we have bonding. So what kind of bonding we are going to see here? So just see. So we have Mn and we have Mn. There is a bonding between Mn and Mn. In between the 2 transition metals we have a bonding, and totally 10 carbonyl we have, 5 for this one and 5 for this one. So how I am supposed to draw? See here, 1, 2, 3. This will be the 4th one. This will be the 5th one, and 5 more for this one. So 1, 2, and 3. 4th one and 5th one. That kind of geometry we have. Mn2CO10. Here we have what actually Mn single bond. In case of CO2-CO8, central metal atom is cobalt and carbonyl will be ligand. Here we have a cobalt as central metal atom. We have 2 cobalt, isn't it? So CO I am supposed to write here. So here there is a bond. There is a one bond between metal to metal. One metal bond we have. So totally 8 we have. So this is the fashion. So carbon monoxide will be in this fashion. So 3 the carbon monoxide, carbonyl will be here, and 3 carbonyl will be here, and we have 2 more, and 2 more carbonyl will be in this fashion. So 2 more carbonyl will be in this fashion. So totally if you count the carbonyls, they are totally 8. So 3 and 3, 1 above and 1 below. But you remember, we have a metal bond in this compound also. We have metal bond in this compound, but the carbonyl this and carbonyl this are completely different. They are not actually the same. So we have these 3 carbonyls and these 3 carbonyls. These we call it as the terminal ligands. Terminal carbonyls we call it as, whereas this particular carbonyl and this particular carbonyl we call it as the bridge ligands or bridge carbonyl. Why these we call it as bridge carbonyls? Because this carbon is related to only this cobalt, whereas this carbonyl is going to be related to this cobalt as well as this cobalt. Therefore bridge carbonyl we call it as, and bridge carbonyl we call it as, whereas these 3 are terminal, and in these cases we don't have any bridge. All the carbonyls are terminal. Of course there is no question of a bridge and a terminal carbonyl in case of the above diagrams, because in the above diagrams we have only transition metal only one, and here we have two. In that case we have metal metal bond, here we have metal metal single bond, and here also we have metal metal single bond, and out of 8, 2 are bridge ligands and remaining 6 are terminal ligands. Whereas in case of this particular compound we have 10 carbonyl ligands, all the 10 are terminal ligands only. That is all about the metal carbonyls and how it has sigma character as well as the pi character. That is the diagrammatical representation, and that is about some examples what I considered. So even though we have more explanation in case of crystal field theory, we have limitations of that. And what are these limitations? Presence of unpaired electrons is going to explain the color property of coordination complex, but actually we have such kind of complexes where we have either completely filled or completely empty d atomic orbital, even though that is going to show a kind of a color property. According to crystal field theory, the bonding between central metal atom and ligand is purely ionic or purely electrostatic, but there is no explanation for covalent character of the bond in between central metal atom and ligand. Ligands are considered as the point charges if you consider anions. So anion, of course, it has minus charge over there, and in case of a general example, we can say the anions are going to be responsible for the greater crystal field splitting, but actually according to spectrochemical series, the carbonyl or the carbon monoxide and NH3H2, they are supposed to cause a greater crystal field splitting rather than anions. So we don't have any explanation for these, and these are termed as the limitations or demerits of crystal field theory. In the higher classes, you will be learning the next theory, that is termed as the ligand-filled theory. That is all about the chapter coordination compounds.